Now I'm going to go ahead and talk about the theory behind my coordination strategy. The first part of any coordination strategy is to capture the conflicts. Over here we have we have multiple resources in the system. These resources are managed using semaphores so that access can be controlled. However, in order to avoid racing conditions, these semaphores are backed up by queues. So whenever a self-management agent wants to send a request or it wants to access the resource, it has to add its request to the queue instead of trying to lock the semaphore as before. Then the coordination agent captures the conflicts mainly by managing the resources, the queues, and the requests. Now we have captured the conflict. In order to resolve the conflict, we need some kind of information. This information is the environment information, and our coordination agent has access to this information. The environment information consists mainly of the system parameters, of the current system state, of the failures, and of the external influence. So now we have the environment information. Then the coordination agent would use this information to resolve conflicts by permitting and rejecting requests. So it receives a request and it sees, would it cause a conflict? If yes, then it would reject it. In order to do that, it implements two mechanisms. The first one is conflict avoidance. So right before the request is added to the queue over here, the coordination agent inspects it and it decides, will it cause a conflict in the future? If it does, I will reject it as a coordination agent. The second mechanism is conflict detection. Using this mechanism, the coordination agent takes a look at the queue right before it takes the request out and locks the semaphore. It checks the queue. Will this request cause any conflicts? Does any other request have higher priority or should gain access? If yes, then it will be rejected. The natural question that arises now is, how can we use the environment information to resolve conflicts? Answering this question took a bit of research and a bit of comparing different strategies, and I found that the best solution that's suited for our situation is a rule-based expert system, which consists of an interpretation engine and a rules and a facts database. The environment information is formulated or is represented as facts. So for example, I could say that robot 1 or 2 has a battery level of 10%. This is a fact. It's in the system and it's a fact. Then I would use the rules for conflict resolution. The rules are formulated in this way. If a certain scenario happens, a certain action has to be taken. So for example, if robot 1 has a battery level of 10% and there are no other batteries, this is a scenario, the certain action, which is like drive it to the depot or drive it en route, should be taken. These rules, however, should be written in collaboration with the field expert, because the system architect usually doesn't know all of the ins and outs about when it comes to the system. So the field expert who knows more about the system should come up with these scenarios. Using a rule-based system, a rule-based expert system, has many advantages. The first one is that it has simple logic. So as you can see, it's more or less an if-else kind of algorithm, and it's very simple. This results in it being very efficient and requiring minimal processing power. Furthermore, it's very deterministic. It's always the case that if a certain scenario is happening, a certain action will be taken. The fourth one is very important, which is the rules are separated. They're kept in a separate database. So if I want to modify the behavior of the system, all I have to do is go into the rules and update them, rather than going inside the system and modifying the code. It also supports fallback rules. A fallback rule is a generic scenario that applies when no other scenarios apply. So we have all these scenarios, 1, 2, 3, 4. If none of them can apply, then I'm going to go ahead and use a generic rule. The generic rule can have an action such as first come, first serve, or reject the request or accept the request. Then the rules enable us to have emergency cases by the means of high priority rules. So if I have a certain emergency case, like in the case of the nuclear reactor, a meltdown, then this gets the highest rule and like it gets executed before any of the other rules. However, a rule-based system, as with any other system, has disadvantages. The one main disadvantage is that all of the scenarios have to be covered in order for the system to be very to be very functional in a correct manner. And this might be very tedious, especially when it comes to complicated systems. Even a field expert cannot sometimes cover all the scenarios. Finally, to the conflict resolution algorithm. In our system, we have now an environment, we have a self-management agent, we have a rules database, we have a coordination agent that contains the interpretation engine. In the first step, the self-management agent would send a request to access the resource to the coordination agent. Then the coordination agent will take a snapshot over here of the environment. So it goes to the environment and takes a snapshot of the current environment and formulates this environment information as facts. Then after that, it would forward the facts to the interpretation engine over here. In the next step, the coordination agent would ask the interpretation engine whether or not a conflict exists. Now, over here in the rules database, we know how to resolve conflicts using the rules. So what the interpretation engine would do, it would contact the rules database and ask it whether or not a conflict exists. Finally, the coordination agent now has the information that it needs, and it can decide whether or not to permit or reject the request and sends the results back to the self-management agent. This brings us to the end of the coordination theory. Now on to the prototype and the live demonstration. During my thesis, I had to implement a prototype. In this prototype, I had to realize a new coordination agent. This coordination agent used clips for the interpretation engine because it's open source. It is very mature. In fact, it was started by NASA in 1985, and it's easy to use. In fact, I started to write code that's related to my system in less than a day after I started learning it. Then the interpretation engine clips was integrated with the coordination agent. So this meant that I had to write clips rules to model the system behavior and and make the system behave in the way that that's described in my design documents. Then the previous self-management agents that existed had to be modified a little bit so that they can interact with the new coordination agent, which meant modifying the withdraw agent and the robots en route agent. Then a GUI was added to control the coordination agent because the coordination agent has multiple parameters like enabling logging or enabling or loading different rules. So a GUI was added to make this easier for the user. Finally, in my new prototype, if any user later on wants to add an extra self-management functionality, first they have to implement the self-management functionality. Second, they have to write the relevant clips rules. Then finally, they have to send a request from the self-management agent to the coordination agent requesting resource access. And then a new self-management functionality, which also was one of my tasks, was written. The purpose of this functionality is to send the free robots to a certain position. So the user decides on a required distance in millimeters, and then the agent looks for free robots and sends these robots to a certain position that's a certain distance away from the route.